Good afternoon, my name is Mathieu Lizet, I'm from Ecole Polytechnique, and I'm going to present our work on problem number 14, solar cell characterizer. So here is our solar cell. So here is the problem. We need to propose and implement a method to determine the irradiance and color temperature of a light source by using solar cell materials. And how accurately can they be measured? So accuracy...
We can't see the...
Oh, I'm very sorry. Okay. Sorry? Yes. How accurately can they be measured, and what are the limitations of our method? And then we are interested in relevant parameters, of course. So now we need first to determine irradiance and color temperature of a light source. So what are these parameters? So color temperature, we choose a definition. Temperature, we define this as it is the temperature of an ideal black body that will radiate the light of the same color. Because we know that a black body has a wavelength which is linked to its temperature by the Wien's law. And we will use this to define the color temperature. Then irradiance, what is irradiance? It is the power which is received by a surface per unit area. So this will be the irradiance. And in fact, with Stefan-Boltzmann law for a black body will give us the irradiance. And in fact, we see that it will depend on the temperature. But as we want to study temperature and irradiance separately, we take a parameter that does not depend on temperature. So in fact, we will take only the proportional coefficient. So we choose this definition of irradiance parameter. So this will be irradiance. So here, our definition fits for black body, I mean, but it can be broadened because it is the color that looks the same, the same color. Okay, so we need to use solar cell materials. So first idea, we could use filters and a photodiode, for example, but in fact, we try to use only solar cell materials, so we take away the idea with the filters. And now, we are going to see what does a solar cell do. In fact, we have photons that come into the solar cell with a given spectrum defined by irradiance and color temperature here, and it gives an output current. So this is what the solar cell does. And what we want to do is we want to measure this current in order to get back to the initial spectrum with irradiance and color temperature. So this is what we are going to do. So first, we need to understand how the current will depend on spectrum parameters. So here, some very basics of solar cell conversions. So if we have a semiconductor with an energy gap, and if a photon with an energy which is superior to the gap goes into the semiconductor, it will going to promote an electron, and this electron will be able to provide energy which is about the energy of the gap. So this is how we get energy from the cell with photovoltaic panels. So, and we use this with our solar cell. So now we want more precision on how the current will depend on incoming light, and to do this we are going to introduce the external quantum efficiency. So what is the definition? It is the probability of getting one electron out of the cell, so this is the current, after sending one photon, the spectrum of wavelength lambda. Okay, so this is really a story of probabilities for one electron and one photon. So we want to measure this quantum efficiency for our solar cell. So we take a monochromatic light which is precisely calibrated. So we take monochromatic by using this this monochromator, sorry, and we send it on our solar cell. And now we can count the electrons by measuring the current. We know exactly how many photons we send in, and so now we know the external quantum efficiency. So this is the external quantum efficiency of this solar cell. We measured it ourselves, and now we know everything about the solar cell. This is very important. We know for any wavelength what the response will be. And this contains a lot of physics about semiconductor that we can talk about in discussion, for example. Now, knowing the quantum efficiency, we can predict the current for a given spectrum. And this will be our method. So now we predict the current. So for the photons between lambda and lambda plus d lambda, so for a given wavelength, the number of photons received is just the power divided by energy of one photon. So we will have here in blue the quantum efficiency that we measured, and here several spectrum in number of photons per wavelength. And then here the number of electrons out will be given by this number of photons multiplied by quantum efficiency, by definition. So here we just multiply the two curves, and we obtain this curve in electron number over the spectrum. And now we can just integrate over the spectrum to get the total current. Now we can predict the output current in the solar cell, and our goal remains the other way around. So how can we do this? So we can measure the currents. This was the goal of our method. And now, what do we know? Okay, so in fact, we see that there are several spectrum that can give us one current. And in fact, this is well represented by these iso-G curves, the isocurrent curves. And in fact, here we have the irradiance parameter and here temperature parameters. And this is given for one measured current. These are all the spectrum that can give us this current in this solar cell using the measurement of quantum efficiency. So now, do we know something? In fact, we don't really know because we have many temperatural colors that can correspond and many irradiance too. So what do we need to do? So in fact, we could have predicted this because we want to know two parameters and we measure only the current. So now we need another solar cell with a different quantum efficiency to measure another current. So we take a different technology. This is silicon. We take another technology, which is gallium arsenide. We measure the quantum efficiency, so the spectral response, and now we have two informations. So we make just the same thing. We integrate over the whole spectrum to predict the current. Now we can predict the two currents for the two solar cells. And now we have two isocurrent curves. So these in blue, in red are the spectrums that can give this current for gallium arsenide, and in blue for silicon. And now we see that in fact we have only one intersection, so we will have only one solution as the input spectrum. So our method, quick review, we take two solar panels, we measure the two currents, we have the two iso-G curves that will cross, and then we get back to the initial spectrum. So we need to evaluate the accuracy of our method. So in fact, when we measure the current, we will have some uncertainty. So how can we put this could we evaluate this? So in fact, we take two light sources with very a little difference of temperature, and we will see, is it possible to separate them with our technique? And in fact, we will integrate this spectrum as always to get the two currents, and the answer will be we can tell apart these two colors if we can tell apart the two currents that we get from this. So this will depend obviously on the precision of our current measure. So now we can represent this on the iso-G curve. So in fact, the uncertainty over the current measure can be represented by giving some width to the curve, width that will correspond to the uncertainty on the measure of current. So now the uncertainty will propagate. We have some uncertainty on the current measure. It will propagate on the parameter description. So we look for this intersection here, but as the curves have some width, in fact, we have some uncertainty which is larger because it has propagated when looking for the intersection. And now we can evaluate our uncertainty. So here uncertainty will propagate and we can evaluate this pretty easily, in fact. So here we see the uncertainty. We are around very good precision of around %. And uncertainty on irradiance, again, several %. So now we want to make a tool to make our method very easy to use. So in fact, we plot an abacus. So here, this is the current that we will measure with the gallium arsenide cell just here. And this is the current that we measure in the silicon cell. And in fact, we just have to take the point that will correspond to these two current measurements, and we get, with this scale, the temperature of color of the source. So using this abacus will be extremely simple. We measure the two currents, we look into this graph, like it's zoomed here, and we get more precision, and we get the temperature of color. So we can do the same for irradiance, of course. So now my conclusion. So we have designed a very simple method. We have only to do two measurements of currents with two different solar cells. We use only solar cell only, as it was suggested by the problem. We have a full prediction of accuracy over the parameter space, as I've shown with this method for propagating the uncertainty from the current measurement that it is here. However, this method might have some limitations. We have a pretty high sensibility to the uncertainty over the current measure, and this is a bit regrettable because of this shape of the curves. And we need also a solar cell of non-silicon technology, which is pretty hard to find. In fact, we had to get in a lab to get the gallium arsenide cell. So these are the limitations. And what's interesting, it is that our method can be adapted to any two-parameter spectrum. Here we had irradiance and color temperature, but we can do this, for example, for a monochromatic spectrum with its resonant frequency, lambda, and its irradiance. So any two spectrum parameters can be measured with our method. Thank you very much for your attention.
This is our opposition to the problem number 14, solar cell characterizer, presented by team of Lyon. Ecole Polytechnique, sorry. Yeah, okay, so let's go to the analysis. What has the reporter done? First, he introduced us the physics behind the problem and what do we have to measure: color temperature and the irradiance. One of them was presented by the black body, I forgot the word, sorry, and Green's law, and the other one with Stefan Boltzmann law, which is a little bit limiting, given that not every radiator is a Planckian radiator. Yes, of course, but this is probably the assumption of the report, and we will discuss it later. Then reporter presented us their method, a very unusual one given what we heard here, because they didn't use any light filters, and they tried to use only solar cell and light source to measure both of the parameters. And what was that? Yes, so the reporter made a very thorough investigation of the parameters of their solar cells, like quantum efficiency and their basically response to the light. And then they proposed a method to measure color temperature and the irradiance only for Planckian radiators. Again, I should mention that. And they estimated the accuracy or the error that they can have, but we haven't seen any experiment or any even estimation in numbers. So we don't know how accurate this method is, what are the limitations, what can this apply to? Well, probably the black body, but what else? And how could this work? We would like to discuss it. What more can I say about this? Okay, that was rather interesting. That you used but it was not clear enough. The report itself was not clear enough in some points, so that we had to clarify this too. And I'm sorry, I don't think I can use all 5 minutes. Probably lower my marks, but still, yes. Let's go to the discussion.
Okay, you can start the discussion.
Yes, let's start the discussion. I want to talk about accuracy and limitations.
Okay. So I
Because I
heard.
think the physics is clear here.
Okay, so I heard what you were reproaching. In fact, it's like we did not do a real experiment, and we talked about only the accuracy for perfect black body. And you're extremely right; it does not exist. It's a model. So in fact, what does it give in real life? So we tried this, of course. So in fact, what we do here. Oh, is it supposed to work or not? Okay, so sorry. So what we're going to do is to make to try to see what it would give with the sun. So in fact, we have a little technical problem, which is that our gallium arsenide cell cannot get out of the lab. So we make this with a simulator, solar simulator, that they use to calibrate the solar cells. So in fact, we make with solar simulator. So here, we calculate the expected values. So we measure the quantum efficiency that we had, and we expect the values of the current that we are supposed to have. We measure the values of current for this spectrum. We measure the current, and we see that the current matches. So it seems that, okay, our assumption of multiplying the quantum efficiency by the incoming spectrum is correct. So, okay, here we are okay. So now, this is the spectrum, in fact, of the solar simulator. It is right here, and we see that it's pretty much different from a Planck spectrum. So here, our method provides the sun temperature prediction of 4,500 degrees Kelvin, and the real sun surface is of 570. And we see that we have much, much larger errors than what we discussed, because we talked only about perfect black bodies. So, okay, so we are not so surprised, but we try to understand why this is not working so well, even though the order of magnitude is quite correct. So in fact, this is in fact the black body spectrum that we predicted, the green one, with our method. We said, okay, so in fact it is a black body. If we assume it's a black body, it will be this one, that's the best fit. And with the real black body of the sun, in fact, it's the red one. So we see it's hotter, as I've shown. And so how do we understand this with our method? In fact, what does our method give? In a nutshell, it finds the black bodies that will best fit in terms of integration of light over the whole spectrum. But this is integration, in fact. So it's not the same thing as just looking at the shape of the spectrum and saying this is the peak value. So we integrate, and in fact, we see that in this spectrum, which is, you will recognize that this is not the real solar spectrum. In fact, these peaks are only in the simulator. They are not in real.
Excuse me, not to make your report 15 minutes long instead
okay,
of 10.
just finish 10
10
seconds. So in fact, yes, I understand. In fact, we just see that these peaks are going to translate the integration to offset. To shift it to the right. And so this is why we have some errors, because we study the integration of the spectrum. Say sorry.
Yes, okay, so as I understand you, that you have basically one value by which you sort of recreate the black body spectrum, right?
Two values.
You by one value, I mean the place where they intersect.
Yes. Oh, yes.
So
okay. Yeah,
that's
one couple, yes, irradiance and color temperature.
Yes, yes.
Yes.
So you recreate the black body spectrum.
Yes.
And sun, again, is pretty close to the black body.
Oh,
So
that depends
close.
if you get inside the atmosphere or outside the atmosphere, of course.
Yes, and what I want to say is that there are a lot of different light sources.
Yes.
Like with spectrum, like a mercury lamp, for example.
Mercury lamp, yes.
Yes, or just the spectrum of hydrogen, or LED.
Yes.
Or LED lamp, again. They are very, very, very different.
Yes, I fear our method.
Can you apply your method to anything of
Okay, in fact,
this, or can you improve your method to make it applicable to this?
okay, so in fact, it's our method, the strength of our method is that it can be very, very general. In fact, we measure a certain number of currents, we measure a certain number of, and then we can get a certain number of parameters on the spectrum. This is where it's interesting. We just have to calculate the spectrums. Like here, we make it with black body, it's pretty easy. But if you tell me, like, you will have some for example, for hydrogen, some rays, I don't know how we say this in English, but some bands where you will have some light, yes, a few peaks, for example. We just have to give this as a parameter, and we take as much solar cells as we want. We need the quantum efficiencies to be.
What if you don't know
thank you, guys.
beforehand?
We can continue this discussion later.
My name is Luca. Thank you for the presentation and the discussion. So, the presentation was really nice. It had a lot of theory and clever ideas. It was a, let's say, simple but very clever idea to use two solar cells because of the two parameters. It seems like it's very accurate. Also, the theory was explained pretty clearly, so I hope everyone understood it. Also, the uncertainty predictions from the current measurements were explained well, but there are some remarks about the spectral limitations, like let's say the maximum frequency which could be measured, and also the parameters. It is not maybe clear from this problem statement if those parameters mentioned are the parameters which you talk about, or the parameters of the solar cell. Let's say maybe some defects in the solar cell or something like that. About the opponent, had a good question about the black body approximation. And also the following discussion was really good. Maybe we could continue on that because you didn't quite tell everything you wanted. Also, the opponent realized the lack of experiment, but the reporter had some measurements in the appendix. Maybe we could spend some more time on that, or we will see if we have time. So first we should, in the discussion, continue where you have ended, and after that we could maybe talk about the spectral limitations, see what you have to say about that, and also the parameters, what you think about the statement of the problem.
The last point that I have heard is that if you know beforehand the spectrum, you can give it as a parameter and recreate it. Like if you know it's a black body, you can, by your two measurements, recreate the black body spectrum. Or if you know if it's not, then you can recreate that. Am I right?
In fact, this is not so a sharp difference. In fact, many lights in common life are close to a certain point to a black body. And our method will integrate the spectrum. If it looks like a black body or not too different, we will have an estimation, which, of course, the precision. For example, if we have a shape like this.
I haven't asked my question yet, and you already are trying to answer.
Okay, I'm really sorry.
My question is, let's look to this light.
Yes.
You don't know beforehand if it's black body.
Yes.
Or if it's like fluorescent lamp,
Yes.
LED lamp, incandescent lamp, anything, just like one wavelength of light.
Yes.
I give you just this light. How can you know which color temperature it has?
Which color temperature it will have? In fact, to answer this question, I think we would have to use some other solar cells. In fact, you can do. In fact, you could push our method very, very far. If you imagine, for example, that your solar cell, if this is the frequency, the wavelength of the incoming photons, and this is the quantum efficiency, so the current response. And if your quantum efficiency is sharp enough, in fact, you will be able to say just, okay, between lambda 0 and lambda 0 plus, I don't know, d lambda, for example, I have this amount of light.
You propose
in
to
fact,
use more solar cells,
yes, you could use more solar cells. And to do this, in fact, you will need, in fact, to tune your quantum efficiency. And this
what
is...
would this give? Like if you use more solar cells, so I think you will get just more curves, if I remember.
Yes,
if
and
understand
so
right.
this will get
What
a
does
little
this-
more technical because you won't make the assumption that this is a black body. So you will say, okay, what I want to know is the amount of light that comes into this region. In fact, it works just like a filter. In fact, the solar cell, this quantum efficiency works like a filter. It will filtrate according to the quantum efficiency. And if you
And
use...
how broad is that? Like how
How broad?
wide
Oh,
is...
yes.
Yeah.
So
Because
here,
it can be, your was from 380
Yes, of
nanometers
course.
to 1.
of course, this
1200.
is
That's a
commercial.
lot.
This is commercial solar cell, so we try to make the largest quantum efficiency. We want to get a lot of energy, but in this case, we're not interested in energy. So in fact, we just want to have this kind of sharp peak. And to
Do
do
they
this,
exist?
no, I don't think so, because no one wants to build this. In fact, it's really not interesting. But for us, it could be interesting. But so how can we make this? In fact, the quantum efficiency will depend a lot on many parameters. So first
Yes,
thing, it will depend on the gap.
So instead of filtering the light, you will just filter the response, basically. Given the, if you have a solar cell with this quantum efficiency and then the other one would be like this. So it's basically like filtering the light, but instead you're filtering the response.
Oh no, I don't know what you mean by filtering the response.
Well, okay, let's
Okay,
leave it.
guys, let's finish. Let's go on the statement maybe of the problem a bit back. So
You want to
do
Oh,
you have-
actually,
do you
there
have-
was a question about relevant parameters,
okay.
which you didn't mention.
relevant parameters?
Yes, I believe that it was in the statement of the problem.
Okay,
Oh, yes,
the
okay.
teams can join the discussion.
Do you mean which parameters do you mean? The dimension parameters or the parameters of the material used?
it is
something
stated in the statement of the
Yes.
problem.
In
What are the relevant parameters?
You're really right
I want
to bring this in, I believe. In fact, the relevant parameters are where the physics is lying. So the physical interest of our method, in fact, it is that it depends really on the quantum response of our solar cell. This is really very interesting physics about how if a photon is exciting an atom and giving rise to an electron, will we get it into the circuit? So first question, if we have, for example, here is a map. So if we have an electron, will we get it back? So this will depend on many parameters, how the electron can move away into the material, what is the distance here that there will be. So first parameters for the electron displacement. Other parameter of the gap, obviously the gap, because if you have not enough energy, you want okay, and so this will depend. This will give you different quantum efficiencies. So you have many parameters. You can also use
one simple question, and then you continue. Do you consider the light source as a relevant parameter?
The light source? Oh no, of course not. We're trying to measure it. No, okay. I was thinking that we want to build a measurement, so the parameters are not what we want to measure.
Okay.
But okay, maybe you think differently.
Because different light sources can affect your accuracy and your measurement.
Yes, you're right. Okay, but I tended to.
This is a relevant parameter, but okay, let's talk about
okay, and so in fact, so we have the materials property. Material property. So at the first rank, of course, the gap property. So we have gap, conductivity, and all this will depend on the wavelength. But in fact, in our method, everything is measured by the quantum efficiency measurement. So everything is contained in our measurement. But if we want to go much further and design our own full spectrum system with many solar cells, we need to consider all this. And so how can we tune our quantum efficiency? So we could try, for example, change the length, the width of the silicon layers, for example.
We can leave that.
Yes. Okay. Sorry.
Okay, you're getting pretty specific. Let's talk. A little about the maximum frequency, perhaps. How does what do you think about the parameters? How could
Maximum again.
What do you mean by maximal frequency?
You measure the temperature. Yes, so you get the temperature from the spectrum of the black body, and if the maximum wavelength is pretty small.
Okay, so I'm not sure I understand, but I try to reformulate and you tell me, okay? So
I think it's not really limited.
in fact, you will need to have some correspondence.
This method, at least.
In fact, if you have your two quantum efficiencies, which are like this, for example, okay, quantum efficiency. In fact, if your wavelength is not if your spectrum is not adapted for this, in fact, for example, you will have a strong peak here, okay, lambda. If your wavelength is not at the right place, you will measure nothing. You won't see the difference between these two measurements. So in fact, of course,
the wavelength, it was about the temperature, I think.
no, but it's okay, frequency.
I wanted to start this discussion about let's say the maximum measurable temperature with your
Yes.
method.
Okay. This is what we're in this.
It's really limited.
No. Okay. Let's say this is temperature, for example, or frequency. Okay. This is frequency. So when you go with hotter black bodies, you go with larger frequencies. Okay. Are you okay with it? Okay. So now, if you take
With hotter, you just get the peak is more like this, and with
no, but it's also
this is the difference. Oh, okay. Well,
yes.
it shifts a little, but still.
No, it shifts a lot. Of course, this is the color temperature is given by the lambda max.
But I agree
Okay,
that your
guys,
quantum efficiency
we have
is
a little
here.
bit time. Let's ask someone else.
Okay.
If someone has a yes.
If you can build your own solar cells, how much solar cells you will use?
It depends what you want to measure. What spectrum? What kind of spectrum?
Any.
Color
Okay.
Color temperature.
Color temperature, but okay. What spectrum? Any spectrum? You don't
Any.
know. Okay. Any
You
spectrum?
don't know.
Okay, so it depends
That's
on the.
actually the problem. You don't know the spectrum.
Okay. Okay.
Let
So.
him finish.
So for example, you could try to, depending on the accuracy that you want, you discretize, it
How
depends
many
on the
solar
accuracy.
cells?
Okay, I don't know, maybe 100 solar
Infinite.
cells. I don't
Infinite
know.
amount.
You take your accuracy and you divide the number of solar cells.
Time's up.
Hello. very simple question. You said you could not bring the cell out of the lab. Couldn't you bring real sunlight
into the lab.
Using a mirror?
I didn't think about this. Maybe it would have been possible, but in fact, I'm not sure. There are several stairs into the lab. No, but really, we could have tried this also, maybe.
Can you go to the slide where you show this temperature measurements of the solar simulation?
Yes.
It was some specific number and I did get lost.
I hope it's going to work pretty
Press something.
fast enough. But okay. Oh.
Yeah, I think you showed it during the discussion here. So it is 4,000 Kelvin plus minus 2,000 Kelvin. Or what?
Oh no, this is mistake. Plus minus 2. No, it's mistake. It's the last significant number.
So
Okay, sorry. So it's plus 20 Kelvin. 20 kelvins.
Plus
like
20 Kelvin.
20. Yes. Sorry. Sorry.
Otherwise, it's better.
Yes, it would be a pretty bad measurement otherwise.
Not taking into account all the discussion about the many solar cells, what is the maximal temperature you could measure with your device?
With our device, okay, we could. In fact, we should use Wien's law, but I don't know all the order of magnitude. I believe. Okay, we need to. In fact, we need to check this in the real measurement. So this is. This is the quantum efficiency. So we take the lambda, and this is the lambda max would correspond to this wavelength. So if a black body has a color temperature which is higher than 300 nanometer, it won't work. So we could use we use Wien's law and we get this. Yes.
You have said that you are measuring current. Could you explain what exactly, was it short circuit current or was it loaded current?
No, short circuit current.
What device have you used with which error and how does it affect the error of the method?
Okay, so maybe easiest question first. How does it affect the error of the method? It's what I've shown with the width on the curves, and so this will increase the error. Okay, second question. How do we measure, with what setup? In fact, we make a 4-point measurement. So we use, okay, no load. No load, it is a short circuit current.
Short circuit, okay,
Yes.
thank you. And
Yes.
could you just switch to the slide while answering the questions with the error, the one you were talking about?
Okay. This one?
The error of the method by the error of the current meter. You have said you had the slide.
Okay. No, I didn't say additional slide about this, but I would have shown.
Okay. The question was how does the error of the current meter affects the error of the method? Okay, sorry, I fear I wasn't clear. Okay, I'm going to go back very quickly on this. Okay, so in fact, as we have slide before, okay, we have some uncertainty on the current. So in fact, the possibilities of spectrum will be much larger because we don't know the current for sure. So we'll have some width on this line, and then as we have some width, the intersection will not be clearly defined. We don't know that this is the spectrum we are looking for. So in fact, we have all these possibilities for possible spectrum, and same thing here for irradiance. So this is how the uncertainty on current propagates to uncertainty on the spectrum. Yes, I just wanted the calculations probably.
Oh yeah, no, sorry, I didn't put it in the presentation. I am really sorry.
Can you please go back to the slide 18?
Yes, slide 18, yes.
So I have a confusion about your method because let's imagine that a hypothetical, I don't know, you have a black body that has a peak, a maximum peak on 300. But you use your method and then the maximum peak you will be away from the regime where you will catch it. But knowing that the shape of the black body will be like that, you will measure it.
Yes, of course.
But then, which will be the temperature that you will read? on that
Oh
measurement?
yes, yes, it will work. If we have a large enough correspondence, for example, if you have this black body and your quantum efficiency is here, you will, okay, put it like
Okay.
this. Yeah, of course it will work because we know the equation here, but you will have less precision, and this is what I show on the precision slides, like here. The uncertainty depends on the temperature.
Okay.
Okay. No, just a follow-up question. Okay, but in that graph, you said that the error will be like 1.3%, but in real life, there, if the peak will be 300, and you will reach something like 400, something like that. Or am I wrong about that?
Oh no, okay, okay. Here again, I wasn't clear. In fact, this error is measured for perfect black bodies, but we have two different cases. In fact, first case, we have not a perfect black body, and second case, we have a perfect black body, but the color temperature is shifted, so we are not exactly here. So this was your first question, and in fact, we will just have an increase in the uncertainty, but so in the second case, that's what I shown with the solar simulator, and we have also increased the uncertainty.
Thank you very much.